is Chen Ming, a postgraduate student from Shanghai Jiaotong University in China. It's a great honor to introduce our work, Oversubscribing GPU Unified Memory, Implications and Suggestions. This paper is an characterization of GPU Unified Oversubscription. I hope it can be helpful. This presentation is divided into 4 parts. First, the introduction and background material can help you have a grasp of this field. Next, the experimental methodology and results is given. Due to its unique features, now GPU is used as a general-purpose processor to accelerate many tasks, and it can often outperform CPU. It is widely used in many fields, for example, in AI, graph computing, statistics, and etc. However, the memory capacity of GPU is limited. This picture shows the main global memory in a GPU board. The onboard memory of a GPU is insufficient, especially for many data-intensive applications. As we can see from the table, as the computing resources in GPU models evolve rapidly over the years, the size of the memory does not catch up as expected. To overcome the shortage of memory, GPU manufacturers provided UVM. UVM establishes a unified address space between CPU and GPU and hides the details of the data migration behind programmers. It has many advantages. First, as the figure shows, it simplified GPU programming. Second, memory oversubscription is supported. This means a GPU can access more memory than the GPU physical memory. It can support memory sharing between multiple GPUs also. Many works studied UVM, but they failed to make deep analysis to reveal the diversity in the trend of performance degradation as oversubscription aggravates progressively, nor the impact of performance tuning strategies on the oversubscription, nor the possibility of utilizing UVM to implement multi-GPU computation. Therefore, we are here. This paper investigates these 3 important topics. In each level, we analyze and offer targeted principles and recommendations that can help developers to design more efficient and robust UVM programs. A workflow of a CUDA program is built up by CPU serial code and GPU kernels. To invoke a kernel, the data should first be copied from main memory to GPU. After the kernel finishes, the result is copied back to main memory. Therefore, data duplication is needed. Under UVM, the data is shared by both GPU and CPU. The data is organized into pages. When a processor accesses data, the corresponding pages is moved from one device to the processor, and the page table is updated automatically. This figure demonstrates a detailed file handling process. And to help developers to do fine performance tunings, CUDA provides some APIs. They are prefetching and data movement advices. Prefetching asynchronously fetch data beforehand when the advice, while the advices tell the driver what the access pattern of the data is. For example, it is read-only data, or mostly accessed by one device, or moves between devices frequently. And this helps the memory manager to better arrange the data. Here is our main idea. We select a wide range of representative applications. First, we investigate how UVM oversubscription affects application's performance in detail. Next, we combine UVM oversubscription with performance tuning methods and multi-GPU. Here is our benchmarks selected. They come from widely used benchmark suits, and we modified them to our UVM programming model. And to quantify the degree of oversubscription, we put forward a concept of oversubscription ratio. When no oversubscription, the ratio is 0. The more oversubscription, the larger the ratio is. This figure shows the application's execution time as oversubscription ratio increases. Obviously, they are different. We can see that applications in C, the curve remains stable, while in A and B, we can observe that, very interesting, the curve keeps steady at first, but after a specific ratio, the execution time have a sudden and dramatic increase. We refer to the ratio as the launch ratio. Also, the ratio is different for different applications. For example, it's 2 for 2 mm. And the difference in launch ratio between applications reflects their sensitivity to oversubscription. The larger the ratio is, the application is more sensitive to oversubscription. And these figures display the pattern of their page faults, both the time and the page when page faults occur. Under oversubscription, the size of the overall dataset is beyond the capacity of the GPU memory at high oversubscription ratios. The working set accesses GPU memory, thus GPU swaps pages to main memory. When the data needs to be accessed again, the page will be moved to GPU again. Thus, some page may fault multiple times, as you can see from here. And the fault pages shows a line-like segmented pattern. We also found that each segment is corresponded to a separate data structure of the application. Here, we take gemm as an example. Gemm is simple. It does matrix multiplication as shown in the figure. It has 3 segments, corresponds to A, B, and C from high to low. We can see the number of pages of page segments of B grows as the ratio increases. Although each element in A, B, and C is accessed once, the order of the accessing is different, which leads to different page fault numbers. For A and C, the elements are accessed row-wise, but B is accessed column-wise, and the irregularity of memory access makes pages in P more likely to fault. And pages that have similar access patterns to with B in gemm could frequently trigger page fault, and we refer to them as 4 pages because they are frequently accessed but have low locality. 4 pages are highly related to the performance of applications under oversubscription. The page faults of 4 pages increase substantially above the launch ratio, and their proportion determines application's sensitivity to oversubscription. So, in this section, we observe the applications have different sensitivity. and the concept of launch ratio and 4 pages is put forward. For UVM performance tuning techniques, we experimented policies of both vanilla UVM and the different combinations of them. And the left figure shows what prefetching and UVM hints affects the execution time of 3 applications. First of all, policies have different impacts. PF and PL have little impacts, while RM causes a significant reduction in performance. Interestingly, we observed that AB had opposite effects when running beyond and above the launch ratio. When under launch ratio, when AB is enabled, the execution time is much longer than vanilla UVM. However, when above the launch ratio, the execution time AB shows to be a preferable policy. For example, for NW, AB becomes 5 times faster than UM on the above the launch ratio. We further set different policies for each structure because the combinations is large. We chose the policies by focusing on the combinations of AB and RM. Here is the result. Without oversubscription, the gap between the policies is negligible. Under oversubscription, the policies that have good performance below launch ratio turn out to be the worst performance above launch ratio. And the good performance policies have one thing in common. They all set the policy of policy AB to B, and the metrics that 4 pages come from. So overall, the effect of hint AB varies in different situations. When the ratio is higher than the launch ratio, setting 4 pages to AB is good, but it harms the application's performance when oversubscription is not high enough. As previously described, UVM enables shared addressing space between multiple GPUs and ensures consistency. To transform a single GPU program to multiple GPU, we split a CUDA kernel into multiple kernels, where each kernel is executed on one GPU and handles a proportion of the original job. To facilitate this transformation, we also provided a sample library. Under this policy, you could discover that using multiple GPUs provide impressive speedup. Compared with a single GPU system, GEMM has nearly 4 times speedup when running on 4 GPUs. We also notice it has the same slowdown above the launch ratio as before, since the 4 pages in B incurs more force as the ratio increases. We also tried other policies like the 2 listed. However, all of them bring severe slowdown compared with the single GPU program, a single GPU system, even under no oversubscription. 4 pages in B causes more pages to thrash, and another reason is our platform limitation. And in summary, UVM is not always good on multiple GPU systems. To make it useful, a job needs to have enough thread blocks to utilize the GPU's computation capacity, and have little memory interference between GPUs. All the interfered pages are read-only. And this page concludes the topics of my presentation. And thanks for your attention.